Hi everybody, in this recording we will be going over section 4.3, Riemann sums and definite integrals. To evaluate the area under the curve for our function f of x is equal to the square root of x for x between 0 and 1 inclusive. So this will be given by uppercase S, which will be equal to the limit as n approaches infinity of the sum from I is equal to 1 up until n, and we'll be evaluating our function at the point ci and multiplying by our delta xi. So in this particular example, we are going to let our ci be equal to I squared divided by n squared, and that will be the right endpoint of the partition. So that means that our delta xi will be equal to our I squared divided by n squared minus I minus 1 squared over n squared, and that simplifies to 2i minus 1 divided by n squared. The partitions will increase in size as I increases. So taking the sum, we evaluate our function at our ci, so the square root of I squared divided by n squared, and there we are multiplying by our delta xi, 2i minus 1 divided by n squared, and we are taking the sum from I is equal to 1 up until n. So upon doing so, we can simplify, and we get that we will be evaluating the sum from I is equal to 1 up until n of 2i squared minus I, and we can take out the 1 over n cubed, and then we know that the sum of I squared is this term right here, and we know the sum of I is this term, so we could just multiply 2 by this portion right here, since we are multiplying by 2i squared. So then we have 2 times n plus 1 times 2n plus 1 divided by 6 minus this sum right here. So that'll be n times n plus 1 divided by 2, and then we still need to multiply by our 1 over n cubed. Now we can take the limit as n approaches infinity, and that'll be equal to 2 divided by 3. So now we'll be going over the definition of a Riemann sum. So we let f be a function that is defined on the closed interval a to b, and we let delta be a partition of a to b, and that'll be given by a is equal to our first point x naught, and that'll be less than x1, and all those next terms will be less than xn, which is our last term, the b. So delta xi is the width of the ith subinterval, so from xi minus 1 to xi. If ci is any point in the ith subinterval, then the sum, we can write it as I is equal to 1 up until n of our function evaluated at the point ci times our delta xi, for ci between xi minus 1 and xi, is called a Riemann sum of our function f for the partition delta. So the width of a partition delta is the norm, and it is denoted by these symbols right here. It looks like the absolute value, but we have two lines. So the norm is this symbol right here, and that is the width of the partition delta. So if every subinterval has equal width, the partition is regular, and the norm is equal to delta x, which is equal to b minus a divided by n. For a general partition, the norm is related to the number of subintervals by, so we have b minus a divided by our norm, which will be less than or equal to n. So we want the partitions to become small. So we take the limit of the norm as it goes to 0 of I is equal to 1 up until n of our function evaluated at the point ci times our delta xi, and that is equal to L, our limit. So now we can define a definite integral. So if a function f is defined on the closed interval a to b, and the limit of Riemann sums over the partitions delta, this portion right here, the limit of the norm as it goes to 0 of each of the sums exists, then f is said to be integrable on the closed interval a to b, and the limit is denoted by, so this is the limit that we just took, and that is equal to the integral from a to b of f of x with respect to x. So previously we had no limits right here, and that's why it was called an indefinite integral. But now, since we have limits from a to b, this will be a definite integral of f from a to b. So the number a is the lower limit of integration, and the number b is the upper limit of integration. So the following theorem provides a sufficient condition for integrability. So if a function f is continuous on the closed interval from a to b, then f is integrable on the closed interval a to b which means that if we take the integral from a to b of f of x with respect to x, then it will exist. So the proof for this theorem is outside of the scope of this course, but it is provided by this link right here, which will be in the slides. So now we will be evaluating the definite integral from -2 to 1 of the function 2 times x with respect to x. So we're going to choose equal partitions. So our delta x will be equal to 1 minus -2 divided by n. So that is equal to 3 over n. And we will be using the right endpoint. So our ci will be equal to -2 plus I times 3 divided by n. So this definite integral will be equal to the limit as our norm approaches 0 of the sum from I is equal to 1 up until n of our function evaluated at the point ci times our delta xi. So we are evaluating our function 2 times x at ci, which was these two terms. So we plug in ci for 2 times x, so we'll have 2 times -2 plus I times 3 divided by n, and our width, our delta x, is equal to 3 over n, so we multiply by that. So we take the sum from I is equal to 1 up until n. We can split these two sums into two different sums. We can split these two terms into two different sums, remembering to multiply 3 over n to both terms. So then now we have the limit as n approaches infinity of 6 over n times, so this was our first sum right here. We just factor out the -2 and we take the sum of 1 from I is equal to 1 up until n. So we know that this sum is equal to n from the previous rules. So then this term will be equal to -2 times n. And then for this sum, we know that the sum of I from I is equal to 1 up until n is equal to n times n plus 1 divided by 2. And then we need to multiply that 3 over n that we had taken out. And then we need to bring down this 6 over n, so over here. So now we can combine like terms and distribute the 6 over n, and we get the -12 plus 9 over n, and we need to take the limit as n approaches infinity. So that is equal to -3. So now we can put things together. So if a function f is continuous and non-negative on the closed interval from a to b, then the area of the region bounded by the graph of f, the x-axis, and the vertical lines x is equal to a and x is equal to b, is given by the definite integral from a to b of our function f of x with respect to x. So we just take the integral from a to b of our function with respect to x, and that is our area. So the proof of this theorem is just putting the previous definitions and theorems together. Using the theorem that we just went over, we know that area is basically integrating our function and then evaluating at our limits. So for our first example, we have the definite integral from 1 to 3 of the function 4 with respect to x. So right here I graphed it. So we have our function y is equal to 4. It's constant, so it'll just be a horizontal line. And then we have our limits. X is equal to 1, so it'll form this vertical line. And x is equal to 3, this other vertical line. And then we are bounding below with the x-axis. So that means that we want to find the area between our line y is equal to 4 and the x-axis, and bounded by these two vertical lines. We see that this shape forms a rectangle, so that means that we are just finding the area of a rectangle, which is equal to length times width. So in our case, the width is 2, because the length between these two limits is 3 minus 1, which is 2. And then our length will be 4 units, because we are bounded between the x-axis and our line y is equal to 4, so that distance is 4. So that means that the area of the rectangle right here will be equal to 4 times 2, which is equal to 8. Now we repeat the process for this second example. So now we have the function f of x is equal to x plus 2, and we are integrating with respect to x and evaluating at x is equal to 0 and x is equal to 3. So we see that this will form a trapezoid. This is our line. It is a linear function. It crosses the y-axis at y is equal to 2, or this is just a standard y is equal to mx plus b form. So this will be our line. And then we are evaluating at our limits x is equal to 0. So we have this limit right here, this vertical line. And at x is equal to 3, another vertical line. And then we are also bounded by the x-axis. So that means we are finding the area right here, which is a trapezoid. So the general formula for area of a trapezoid is 1/2 times the height times the sum of the two bases. So times base 1 plus base 2. So our trapezoid is kind of on its side. We see that this will be base 1, so the length of that base is 2, and this will be base 2. The length of that is 5, because if we plug in 3 for this point right here, we get 3 plus 2 is equal to 5. So that's how we were able to get the length of this second base. And then our height is 3 units, because we are evaluating from x is equal to 0 to x is equal to 3. So right here we have 3 for our height. So then we can just carry out these operations. We have 2 plus 5 is 7, times 3 is 21, times 1/2 will give us 21 over 2. So that'll be the area of the shaded region that is bounded between this function, x plus 2, and the x-axis, and bounded at x is equal to 0 and x is equal to 3. Now we have definitions of two special integrals. So for our first definition, we have if a function f is defined at x is equal to a, then the integral of f of x with respect to x evaluated from a to a will be equal to 0. If a function f is integrable on the closed interval from a to b, then the integral of f of x with respect to x, evaluated from a to b, is equivalent to now switching the bounds. So now it'll be from b to a of f of x with respect to x, but now it'll be negative. So this just extends the definition of the integral, and we have some examples here. So for this first example, we have the integral of sine squared of x with respect to x. So we integrate and we evaluate from pi to pi, that is equal to 0. Now if we integrate ln of x with respect to x from 7 to 3, that is equivalent to integrating ln of x with respect to x and evaluating from 3 to 7, but now it'll be negative since we switched the bounds or the limits. Additive interval property. So if a function f is integrable on the 3 closed intervals determined by a, b, and c, then if we have the integral from a to c of f of x with respect to x, then we can break that interval into 2. So now it'll be from a to b of f of x with respect to x, plus the integral from b to c of the function f of x with respect to x. So this was just the entire interval a to c, and b was a point in between, and we just cut it into 2 integrals. So to prove this, notice that since the definite integral is the area of a region, it must be the sum of 2 regions that add up to it. So here we have an example. We are taking the integral of the absolute value of x with respect to x, and we are integrating over -1 to 1. So we can break this up into the integral of the absolute value of x evaluated at -1 and 0, plus the integral of the absolute value of x with respect to x evaluated at 0 and at 1. So that'll give us 1/2 plus 1/2, which is equal to 1. Now we have properties of definite integrals. So if the functions f and g are integrable on the closed interval a to b, and k is a constant, then the functions k times f and f plus or minus g are integrable on the closed interval a to b. And we can say that the integral from a to b of k times f of x with respect to x is equal to taking out our constant k and multiplying it by the integral from a to b of f of x with respect to x. Now, if we have the integral from a to b, and we are taking the sum of f of x and g of x, or the difference of f of x and g of x, then that is equivalent to breaking this sum into the sum of 2 integrals, or this difference into the difference of 2 integrals. So if we were adding f of x plus g of x inside the integral, then we would have the integral from a to b of f of x with respect to x plus the integral from a to b of g of x with respect to x. Now the same concept applies to the difference, but now we are subtracting. We have the preservation of inequality. So if the function f is integrable and non-negative on the closed interval a to b, then we have that 0 is less than or equal to the integral from a to b of f of x with respect to x. Now if the functions f and g are integrable on the closed interval a to b, and f of x is less than or equal to g of x, for every x in the closed interval a to b, then we have that the integral from a to b of f of x with respect to x is less than or equal to the integral from a to b of g of x with respect to x.